So today we're going to be talking about Newton's third law of motion. So as we've been working through this unit on forces and how they affect the motion of objects, we've obviously been focusing on Newton's laws of motion. Newton's first law: an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. That law allows us to predict what it's going to take in order for us to change the motion of an object. As we've been discussing, you have to have a force that is unbalanced in order to make that happen. How much of an effect that unbalanced force has on the motion of the object, the changing motion of the object, is Newton's second law. As the mass of something increases, it's going to take an increasing amount of force in order to cause it to accelerate. So the more massive something is, the greater the force is going to be required to cause a greater change in the object's motion. Now, what we haven't talked about so far is the nature of the interaction between the two objects. You have, anytime a contact force is being imparted on something, okay, you grab a door handle and you push a door open. That's a contact force. You, as the person pushing on the door, are in contact with the door, but you're interacting with a second object. And so Newton's third law is really all about how the forces are exchanged between the two objects that are interacting. So, for example, when you punch a wall, why does it hurt your hand? We're going to talk about that. Or if you were to, say, kick a big rock, why do you hurt your foot? Or maybe you play baseball or softball, and when you hit the ball with the bat, you can feel the interaction in the bat. Well, why is that? Okay. In order to understand this, we have to talk about force pairs. Okay. So, the key thing to remember is we're talking about pairs. We're always talking about two objects. So, say as we're talking about Newton's third law and force pairs, we're going to be focusing on the interaction between the two things that are either exchanging contact forces or the two things that are interacting over long range, say like gravity. Definition of gravity, once again. Any two objects that have mass exert an attractive force on each other. That's also going to be a force pair. So let's go to this example. I'm sure in moments of frustration, we've probably punched something, and so maybe punch a wall. So if we look at a person who punches a wall, when you hit the wall, are you applying a force on it? Well, yes, you're making contact, you're pushing on the wall. The punch is really just a push. And so if we look at the example here, if you were to take your fist and punch this big brick wall, you would be imparting a force on the wall. There would be a force on the wall by your hand. Okay, you are pushing on it. Specifically, based on the drawing here, you are pushing on the wall to the right. Okay. Now, you are the one who is instigating the whole scenario. You are taking your fist and you are making physical contact with that wall. So if you're the one who's doing the punching, why, if you punch the wall hard enough, are you going to hurt your hand? Well, if we reverse the scenario, yes, you might be making contact with the wall, but the wall is also making contact with your fist. And so as you go to punch the wall is going to apply a force back on your hand. So we have a force on your hand by the wall. So really we're looking at the forces between two objects, force pairs. You notice in the top example, the hand was imparting a force on the wall to the right. And now in this second example, we have the wall imparting a force on the hand going back to the left. But again, two objects exchanging forces. You may have also noticed in this moment of frustration that the harder you hit the wall, the harder the wall hits back. So if you just kind of bump into something, make a small amount of force onto an object, you feel that interaction, but it's not that big a deal. But if you were to, say, punch a brick wall really, really hard, you could get really, really hurt. Okay, you could break your hand very easily. And so the harder you hit the wall hits back. Again, we got two objects exchanging forces against each other, and the net result could be that that results in a really big ouch. So don't be punching walls. So this idea that when you have a force being imparted on something, that the object that the force is having or is being applied to, applies a force back. This is Newton's third law of motion. Newton's third law of motion is really all about how forces end up being exchanged between objects. So, to define Newton's third law, reads like this. When an object exerts a force on another object. So right there in the first part of the definition, we got two objects. We've got object one. That object exerts a force on another object, object two. The second object exerts a force that is equal and opposite to the first. So a hand applies a force to the wall. The wall applies a force back on the hand of the same magnitude, which is why if you punch that wall harder, it's going to hurt your hand more because there's going to be more force being imparted back on your hand. And they occur in opposite directions, which we also see in the example. The hand is applying the force to the right, the wall is applying force back to the left. Okay. Now, even though these two objects are exchanging forces that are equal and opposite, it does not mean that they have equal effects on the two objects. You know, if we just look at the example of the hand on the previous page, if we compare its mass to that of the brick wall, I think it's pretty easy to say that the mass of the brick wall is going to be greater than the mass of the hand. Well, mass plays an important role here. Because if we go back to Newton's second law of motion, the change in motion for an object is based on the force and the mass. We're having the same amount of force applied to the wall that we're having applied to the hand, but they have greatly different masses. This is why if you punch a wall really, really hard, you might be applying a big force, but that big force is probably not going to have much of an impact on that brick wall, but it could very well have a big impact on your hand and your wrist. In fact, several years ago, there was a student who, in a moment of frustration during gym class, punched the brick wall down in the gym and broke their hand and their wrist. So that happened to them because their hand has a small mass. The wall, totally fine. Here's another good example of Newton's third law of motion. We've looked at gravity being the unbalanced force acting on things. We know that if we have two objects such as the soccer ball and the earth, two objects exert an attractive force on each other because they both have mass. So if we took the soccer ball and we released it, it would fall and accelerate towards the ground because gravity is being imparted on the ball by the earth. There's the attraction between the two things. But the force of attraction happens for both objects. So as far as the earth is concerned, there's gravity being imparted on the earth by the ball. So we have the interaction between the soccer ball and the earth. We have an equal amount of force. The force of gravity on the ball is the same as the force of gravity on the earth, and the ball gets pulled down and the earth gets pulled up. But even though they have the same amount of force, do we get the same effect on those objects? And the answer is no. When you release the soccer ball, we don't feel the earth go flying up to hit the soccer ball. We see the soccer ball go down towards the earth. Well, the mass of a soccer ball is about half a kilogram. It's about 1 pound. The mass of the earth is written here on the bottom, and that's a very, very big number. It equates to an earth mass of 5 billion trillions of kilograms. So in other words, the mass of the earth is significantly larger than that of the soccer ball. So go back to Newton's second law. You have an equal amount of force being imparted on both of these. However, the mass of the earth is much, much larger. So we have force over mass equals acceleration. The mass of the earth is so big that we are not going to witness any appreciable change in its motion. However, that same force being applied to the soccer ball definitely going to make a change to that object's motion, and it immediately accelerates towards the ground at 9.8 meters per second every second. But it doesn't change the fact that there are forces being exchanged. We have force pairs, force between the ball and the earth. Gravity pulls the ball down because of its interaction with the earth. The ball is pulling up on the earth because of its interactions between the ball and the earth, but we get much different effects based on the masses of those two objects. Here's another example of force pairs, something that you might be interested in with our upcoming Great Balloon Race activity. Talked about how a balloon, if you inflate it and then release it, goes flying through the air. So why do balloons do this? Well, it's an example of rocket propulsion. In other words, the fact that the balloon flies forward when you release the stem and the air can come out, it's no different than a rocket flying through the air. Okay, same theory. Now, it's all about Newton's third law and force pairs. In this example, though, the two objects are the balloon and the air inside. Air is matter. It's made up of stuff. And so, yes, air also counts as an object. Well, you inflate the balloon and then let it go, we can see the balloon shrinking, squeezing down, and we can hear the air being forced out through the little nozzle. So that gives us the force on the air by the balloon. The balloon is collapsing, it is squeezing, it is pushing the air out through that little nozzle, and so there's a force going to the right. Newton's third law of motion. When one object imparts a force on another object, so the balloon is applying force to the air, pushing it to the right. The second object, in this case the air, has to impart an equal amount of force in the opposite direction on the first object. So if the balloon is pushing air out to the right, that means that the balloon is pushing the air out to the right, then the air has to be pushing the balloon to the left with an equal amount of force. And so we have the force on the balloon by the air, and that's why the balloon goes forward. Okay. This is exactly how rockets work, and this is why they use rockets in outer space. And they don't use other means of propulsion, because once you get into outer space, there's nothing to push off of, there's nothing to launch off of. Those rockets burn fuel, they push gases out through the back end of, say, the space shuttle, and that propels the space shuttle forward. Exact same thing that's happening here with the balloon and the air. But again, two objects exchanging forces. So balloon and the air, they're exchanging forces. The balloon is applying force to the air is applying force to the balloon. Once again, they're equal amounts of force in opposite directions, but because of their different masses, we get very different effects on the motion of each. So that's really the basis for Newton's third law of motion. We know that in order to change the motion of an object, you have to apply an unbalanced force. We know that that unbalanced force is going to cause a change in motion. How much the motion changes depends on the mass. That's the first two laws. Newton's third law is all about when you have those two objects interacting, exerting force on one another, what is the nature of that force? The forces exchanged between any two objects are equal in magnitude. It's the same amount of force, but the objects are applying it on each other in opposite directions. So that's it. If you missed anything in the video, please feel free to go back and rewatch. I also posted another video on Google Classroom that you should watch that talks about Newton's third laws, and you can see kind of the mass effects between those two objects interacting. It's a very good video, so make sure you watch that. And then you'll be getting Forces Worksheet 4 that you have time to work on, and that worksheet is due on Monday. We will be reviewing that, and I think getting started on the Great Balloon Race. We'll see. We'll see where Monday takes us, but for sure we will be getting into the Great Balloon Race sometime next week. All right, have a good day, and we will see you then.